Welcome to WXTV, your online source for weatherization training. This is part 3 of our Boiler Basics series, and in this last segment, Mike is going to break down the external components of a boiler system and how they function.
Okay, at this point, I think it's important to explain the external components of a boiler. I try to split a boiler up into 2 parts. The boiler is itself. It has its own things that you need to worry about. And then you have everything external to the boiler. And depending on the type of heating system, you can have a whole bunch of bells and whistles here. This is a pretty simple system. It's a 2-zone baseboard heating system. Here's one of the zone valves and here's the other zone valve. You can get into systems that have, and it's one temperature. Whatever temperature the boiler runs, that's what temperature we send. The way this system runs, our return water is coming here, down each one of these, through this pipe, down this pipe, through the back, into the bottom of the pump. The pump is right here. So the pump is pulling here, and then the pump pushes water into the boiler. It gets heated up. Then the hot water comes out of the boiler, up through here, through this is an air scoop, and out to the zones. We have 2 zone valves, and so that means there's a thermostat that runs this zone valve, and there's a thermostat that runs this zone valve. Both zones could be calling at the same time. All that means is that both of these valves are open. The pump now will pump some water through this zone and some water through this zone. They're piped in parallel. Or one zone could be calling just one, and the water is being pumped through that one zone. If you have a mechanical thermostat, you set the heat anticipator on the mechanical thermostat to the amperage draw of the zone valve. On a forced air furnace, you typically set it to the amp draw of the gas valve. That's one of the differences with multi-zone pieces of equipment, is you set it to whatever device the thermostat is controlling. In this case, the thermostat controls the zone valve. It allows the motor in the zone valve to open the valve. In this house, we have digital thermostat, so we don't even need to set the heat anticipator. Okay, this is our air scoop, and this is an auto air vent. Basically what this does is it removes any oxygen that is in the heating system. We want to get rid of all the oxygen because, number one, oxygen helps keeps rust from forming. What we really want is a dead water in here with no air pockets. So as the air moves across here, there's a little scoop. Any bubbles that are riding on top get scooped up and pushed up to the top. This has a float in it. When it's full of air, the float drops and allows air to come out of this port right here. So it's critical that these little caps are loose. You don't want them tight, because if they're tight, then it shuts that off and the air it just collects in here and it can't be released from the system. This component over here is the pressure regulator. This is our house pressure, which typically is 60, 75 psi on this side. It reduces the pressure over to this side to 12 psi. So anytime the water pressure drops below 12 psi on this side, this automatically adds some water. This is a closed system, so it really is a rare occurrence when that does happen. You don't want to add a lot of water to a system. You want to look for leaks and fix leaks. Raw water is hard on a system. You want to get the water in one time and minimal water being added. One thing that this doesn't have is a backflow preventer. That would prevent any water from potentially going from here into the drinking water of the house. Depending on what your codes are, where you're located. In this particular case, this homeowner is on a well. And when you're on a well, you don't have to have in this area as stringent of a backflow prevention. At the minimum, this would take a Watts 9D backflow preventer. A lot of places would require a reduced pressure backflow preventer. But it really should have a backflow preventer of some sort. The next piece we want to look at is this expansion tank. This is one of the most overlooked pieces on a heating system. If you take a look at here, this little diagram right here kind of gives you an idea of what it is inside. On one side of the bladder is water, and on the other side of the bladder is air. So we have this rubber bladder that separates the two. Well, what this does is it absorbs pressure that is created when we heat up water. When we heat up water, it expands. And water is non-compressible, so it can get to very high pressures. So what this does is it absorbs the pressure that's generated as the water heats up. So as we heat water up, it has a place to go, which keeps the pressure in the system pretty consistent. This particular expansion tank is pre-charged to 12 psi, which means we would also want our pressure regulator at 12 psi. So everything starts at 12 psi, and then we heat water up. As it expands, this absorbs some of that expansion. One of the ways we test this is on the bottom there's an Schrader valve where you can add air to this system. Okay, it looks like the valve on a bicycle tire. And what I do is I just barely hit this, and if water comes out of it, then that tells me that the bladder has a hole in it. I can also tap on it sometimes until I have a hollow sound here, I have a water sound here. But really the sure way is to just tap this thing, and I got air, I didn't get water. That tells me that the bladder doesn't have a hole in it. If the bladder gets a hole in it, then this thing fills up with water. This thing adds water till everything's full. And what happens is the boiler fires up, it heats up, the water expands, and it has no place to go because this water's heated as well. And what happens is the pressure starts to climb. It climbs above 30 psi, and then we start losing water out of our pressure relief valve. Okay? And once we get around 30, water starts going out of that. And it's a chain reaction. Then we add more water. And when it shuts down and cools off, it heats up, it gets to a high pressure, and we just keep running new raw water through this over and over. And in this case, the drain for the relief valve is down in the crawl space. So you really wouldn't know if it was occurring. It would be nice if the drain for the relief valve went into a pan, and then you could see when that happens. That would be a better way of having it than the way it is. Another thing I've ran into is when you buy one of these pressure tanks, when they're pressurized, and I've seen this on certain model numbers, not necessarily the Model 30, but different model numbers, maybe they pressurize them to 12 psi at sea level, and then you bring them up to a high elevation like this, like 5,000 feet elevation. Well, what happens is that pressure is no longer 12 psi, it's a higher pressure. And so then if you don't even check it before you install this, and you just install it assuming that that's correct, now you have a higher pressure expansion tank. And what happens is, because of that high pressure, it can't absorb as much expansion, and that may cause you to lose water out of your relief valve. Your pressure might get too high. So it's critical to check the pressure on these before you install them. The other trick is you cannot check the pressure on these reliably when the system is pressurized. You need to check it when it's not pressurized. So in order for me to set the pressure for this, I need to relieve the pressure on the boiler, get it down to 0. I take just like a tire gauge, put it on here, and I check my pressure. If I'm below 12 psi, then I add a little bit of air to get it to 12 psi, and vice versa. If I'm above, I let a little air out.
Well, that's it for another episode of WXTV in our Boiler Basics series. Thanks, Mike, for all that information. I think there's something there for the beginner all the way up to the seasoned HVAC technician. And thank you for watching.